We're surrounded by data, numbers on a screen, stats in a report. But what if I told you that inside those numbers, there are hidden stories, secret patterns just waiting to be found? Well, today, we're going to be data detectives. We're going to crack the code and uncover the plots hidden in the world all around us, using some really powerful math that works for everything from, say, biology to finance. All right, so here's our game plan for this investigation. First, we'll look at a puzzling pattern. Then we'll grab our detective toolkit. We'll meet the usual suspects, find that first big clue, and then we'll crack the code. And the best part, we'll use all that to actually predict the future. Let's get into it. Okay, so every good investigation needs a mystery, right? And ours starts right here with a simple set of numbers. And honestly, at first glance, they don't look like much. So here's our case file. We're looking at the growth of a wildflower population. Now check this out. At 10 weeks, you've got just 31 flowers. Barely anything. But fast forward to week 30, and that number has just exploded to over 6,500. Whoa. Clearly something is making this population grow, and grow fast. Right now, it's just a table of numbers. But is there a story hiding in there? A predictable pattern. Something that could tell us what was happening between those measurements, or maybe even what's going to happen next. That's the mystery we're here to solve. So, to crack this case, any good detective will tell you you need the right tools. And when you're dealing with data, there's one tool you should always reach for first. It's the most important one. And here it is, the number one rule, what all the statisticians say, is to always create a scatter plot first. Why? Because our brains are just wired for visuals. A scatter plot turns a boring table of numbers into a picture, letting us see patterns that are pretty much impossible to spot otherwise. It just makes it all make sense. And this whole process, taking that picture of the data and then finding the exact mathematical equation that fits its shape, well, that has a name. It's called regression analysis. It's basically how we translate that visual pattern back into a super powerful formula that we can use to make predictions. You see it everywhere, from science to economics, you name it. Okay, so let's meet our key suspects. These are the common shapes, the common patterns that data tends to fall into when we put it on a graph. And here they are, our three main profiles. First, you've got your classic straight line. That's a linear model. Then you've got this U-shape, which you might know as a parabola. That's our quadratic model. And finally, you have this sharp, really dramatic curve, and that's the exponential model. So for our investigation today, we're really going to focus on these two, the quadratic and the exponential. The quadratic one, the U-shape, that's for things that go up and then come back down. Like when you throw a ball, it makes that perfect arc. But the exponential model, that J-shaped curve, that's totally different. That's for things that just grow faster and faster and faster. They keep accelerating. Sound familiar? Kind of like our wildflowers, right? So, the big question is, how do we find our first real clue? How do we know which one of these suspects, which pattern, is the one that matches our data? Well, it's actually a pretty simple three-step process. Step 1, list your data. Hey, we've already done that. Step 2, make that scatter plot. And step 3, you just look at it. You look for the shape. It's like a detective trying to spot a familiar face in a crowd. We're just looking for that characteristic shape.
Okay, enough talk. Let's actually do this. Let's apply these steps and finally crack the code on this wildflower mystery. Time to get our evidence up on the board.
So, when we take those wildflower numbers and actually plot them, wow, the pattern is just undeniable. It's definitely not a straight line. And it's not that U shape that goes up and comes down, so we can rule out the quadratic suspect. No, what we have is that classic, dramatic, sweeping J curve. That's our smoking gun right there. It points straight to an exponential model. Okay, so we've identified the shape, but how do we get from a shape to an actual usable formula? Well, this is where we let technology do the heavy lifting. We use a graphing tool, maybe a calculator or some software, and it can take that visual pattern and just translate it into a precise mathematical equation for us. And when we feed our wildflower data into that tool, this is what it spits out. This equation right here. This is the secret code that perfectly describes our population's growth, where Y is the number of flowers and X is the number of weeks. Pretty cool, huh? Okay, great. We have an equation. But hold on. Any good detective knows you can't just jump to conclusions. You have to verify your findings. I mean, how reliable is this thing really? Is it a good fit or just kind of close? To figure that out, we look at this one special number that the tool gives us. It's called the correlation coefficient, but everyone just calls it R. And R has one job: to tell us how well our equation actually fits the data points. And the rule here is super simple. The closer R gets to 1, the stronger the relationship, the better the fit. And since our R value is 0.9965, well, that's about as close to 1 as you can get. So we can be super confident that our exponential model is a very strong fit for our data. Case closed on that. And this is where all our detective work really pays off. Because we haven't just described what happened in the past. The real power here is that we can now use our shiny new equation to predict the future. So let's try it. If you remember our data, it jumps from week 15 straight to week 20. So what about week 18? Can we use our model to peek into that gap and see what was likely happening then? It's actually really straightforward. All we do is take our equation, and where we see that x for weeks, we just plug in the number 18 instead. Then it's just a matter of crunching the numbers. And there it is. The answer is about 289. So our model predicts that at week 18, we would have expected to find around 289 wildflowers. Think about that for a second. We just used a pattern from the past to make a specific prediction about a moment in time we never even measured. That is the power of regression analysis. So there you have it. We cracked the case of the wildflowers. We turned a boring old table of numbers into an actual predictive tool. Which brings me to one last question, and this one's for you. If you could be a data detective, what hidden pattern out there in the world, what mystery would you want to solve next?